Pixel art has an unusual resilience. Despite being born from the technical limitations of early hardware, it has outlived most of the systems that defined it. Blocky sprites, dithered shadows, and tile-based environments weren't aesthetic choices at the time, but instead engineering compromises. And yet, those constraints gave rise to a distinctive visual language that persists, not just in games that evoke nostalgia, but in modern work that uses pixel art deliberately and fluently. This constraint fosters a kind of visual literacy in both the artist and the viewer, a shared understanding that what's shown is only part of what's meant. The rest is implied, suggested, and filled in by imagination. In order to do this, we have to work against the grain of modern hardware. The goal is to define a process in Unity that can take a 3D scene and produce a stylized aesthetic, one that goes beyond a simple low-resolution filter to evoke the fundamental feeling of pixel art. The reason to use Unity is to not get bogged down in building everything from the ground up. Ultimately, engine technology is a means to an end. At some point, we need to use it so that it can be in the hands of the players. Whilst it is tempting to settle at simply rendering nice pixel art scenes, the true realization of this technology only occurs when we marry it with complementary gameplay. Rendering in 3D gives us a fundamentally different kind of leverage. Once an asset is modeled, textured, and shaded, even in a stylized, low-resolution way, we can animate it, light it, and reorient it freely. The camera can move without needing a custom sprite for each perspective. The lighting can shift to reflect time of day or gameplay events. Objects can cast shadows, receive reflections, and respond to physics without needing bespoke 2D approximations. When an image is scaled, new pixels must be assigned color values, and bilinear filtering does this by sampling the 4 nearest texels around a given UV coordinate. It then performs weighted linear interpolation based on the subpixel offset, blending the color values proportionally. This means that if a target pixel lies between texel centers, the GPU calculates a ratio and mixes the adjacent texel colors to generate intermediate values. While effective for natural images, this process destroys the crisp, grid-aligned aesthetic of pixel art by smoothing sharp edges into unintended gradients and introducing colors that never existed in the original asset. We can see using this fruit bowl scene that simply lowering the resolution and enlarging the render to fill our screen does not result in a crisp image. To bypass this interpolation, we have to be deliberate about when we intervene in the rendering pipeline. Unity provides various injection points, stages like the opaques, the skybox, or post-processing, each offering a different view of the rendered scene. We want to execute our logic after the solid geometry is rendered on the camera's target, before we begin our reconstruction. And so all of this points to the need for a deliberate rendering pipeline, one that doesn't just scale an image, but instead reconstructs the scene in a pixel-conscious way. To fix this, we have to bypass the GPU's interpolation entirely. We implement a 2-stage render pass. First, we downsample the entire scene to a fixed target resolution using point filtering. This locks the pixels into a discrete grid. Every pixel in the low-resolution buffer contains the exact color value from the corresponding source. Second, we upscale that buffer back to the screen. Because we're using a point clamp sampler, every texel maps exactly to a uniform block of pixels on your monitor, preserving the hard edges we established. And so we're able to avoid the muddiness we see here using the original bilinear method, such that the identity of this checkerboard pattern is preserved. We can see in the code that doing so is fairly straightforward, implementing a scriptable render pass to place the low-resolution texture in a handle for use later. Looking at this in action on the fruit bowl scene, this time flat shaded, we can see that boundaries between objects are crisp. There's no bleeding between colors, and meshes, even at this low resolution, are easily distinguished. And whilst what we have captured here is in the form of pixel art, the key shapes of a scene, the aesthetic and feel of pixel art is still missing. To try and find that missing piece, we'll look at how each pixel's color value is chosen. One of the defining features of classic pixel art, and one of its most enduring aesthetic hooks, is the use of a limited color palette. Originally, this wasn't an artistic decision, but instead a hardware constraint. Early systems like the NES, Commodore 64, and Game Boy had strict memory and bandwidth limitations. The NES, for instance, could only display 54 colors total, with just 25 on screen at once. Artists had to build entire worlds under these rules, carefully selecting colors that could multitask. A single shade of brown might serve as earth, shadow, and skin tone depending on context. In modern pixel art, these constraints are often embraced deliberately, even when hardware no longer demands them. Artists choose 16 or 32 color palettes to keep a cohesive feel to the render. The right palette can define the emotional tone of a game, its readability at a glance, and its visual consistency across dozens or hundreds of assets. For a 3D pixel art renderer, honoring this tradition means going beyond just rendering at a low resolution. It means quantizing, deliberately reducing the output color space to match a hand-chosen palette. This isn't as simple as clamping RGB values. It requires mapping arbitrary lighting and material outputs to the closest perceptually meaningful color in a limited set. When we quantize a 3D scene to a limited palette, a naive approach would be to use Euclidean distance. We treat RGB as a 3D coordinate system, a unit cube. You can visualize it like this. Each color is a point inside a unit cube, and finding the closest palette color just means finding the nearest neighbor in that space. The math is correct, but the vision is wrong. Human eyes don't see color as a uniform cube. We are much more sensitive to green than we are to blue, and raw RGB space is not perceptually uniform, meaning equal numeric steps do not correspond to equal perceived changes in color. More critically, RGB distances ignore luminance sensitivity, chroma compression, and nonlinearities in how our eyes respond to hue variation. This is especially damaging in pixel art, where local contrast and subtle hue gradients carry disproportionate weight in visual structure. To fix this issue, we need to move to a perceptually uniform color space, something which is able to adapt to the discrepancy our brains receive from our eyes having a disproportionate response to green light. In the mid-70s, the International Commission on Illumination developed OKLab. Unlike RGB, this space is designed so that equal distances between numeric values correspond more closely to equal changes in human perception. In lab, color is described by three coordinates: L for lightness, A for the green to magenta axis, and B for the blue to yellow axis. Converting our image to lab is computationally heavier. We have to linearize our RGB values, convert to CIE XYZ, and finally map them into lab using a nonlinear transformation that mimics our cone response. Thankfully, the per-pixel calculations are relatively straightforward and can be done in a highly parallel manner on the GPU. We can see the code for both RGB and LAB conversions here. And fortunately, the math for this is all publicly available. To implement, we can translate these formulas into our code. Looking at the three renders side by side, I do feel the CIE colored image gives off the most artistic intentionality. Whilst there are still areas of the image where you might question the pixel choice, this is just one of the trade-offs from working in 3D. Regardless, I do think it is a large upgrade from the RGB space render. Because we've abstracted our quantization into a perceptual math problem, the look of the game is no longer baked into the assets themselves. The color identity of the image becomes pure data on the GPU, a small array of values that can be swapped out at any moment. This gives us immense control over the tone of the game. By providing the render pass with a different set of colors, the image can be altered to create an entirely new look. And that covers most of what I wanted to discuss in this introduction to 3D pixel art. What we've gone over here is the core of our render pipeline, from mesh to stylized render, but there's still plenty more I want to explore in future videos, including additional render passes for outlines, lighting, reflections, and more. If you've made it this far in the video and would like to support the channel, please consider liking and subscribing. It really does help. And as always, thanks for watching.